So this section talks about operator method. This is just another method to solve differential equations. So all we have been trying to learn is how to use Laplace in the previous chapter to solve differential equations. And this chapter we are going to learn how to use different methods to solve ordinary differential equations. So this works when we have simultaneous ordinary differential equations. And so the solutions for the system of the ordinary differential equations, so solutions for the system, a system of differential equations, are written in the form x equals f of t, y equals g of t, depending on how many equations, z equals h of t, and this can go on and on. Those solutions that satisfies each equation of the system on some interval I. And before we look at systems of equations and how do we solve them using operators, so just so you know, the notation here for operators, which I did it in a previous section and it was not required. So x prime, you can write it as dx. That's another notation to write the first derivative of x. X prime is dx. Here the operator is d. D is the operator. And this operator represents the derivative. So if you have x double prime, that would be d square x. If you have y prime, that would be dy. If there's y double prime, that would be d square y. And to solve, if we look at an example, to solve system of equations, differential equations, say x prime plus y prime plus 2y equals 0, and x prime minus 3x minus 2y equals 0. So let's say we have this system of differential equations. What we need to do, we first write it using the d's. Okay, using the d's. So for x prime it's dx, for y prime is dy plus 2y equals 0. For x prime is dx, 3x stays the same and 2y stays the same. So that's the system in terms of operators. And now what do we do? Keep the dx the same. We can factor a y out, so d plus 2y equals 0. This stays the same. Sorry, we factor for the x's, it's d minus 3x minus 2y equals 0. So this is the system that we are required to solve. To do that, we use elimination. Either you eliminate the x or eliminate the y. So let's say I want to eliminate the y. To eliminate the y, I need to multiply this by 2 and this by d plus 2. So we can eliminate the y's. The first one becomes 2dx plus 2 times d plus 2y equals 0. And d minus 3 times d plus 2x minus 2d plus 2y equals 0. Add them up, these cancel out. So what do we get here? We get 2dx plus d minus 3 times d plus 2x equals 0. If we add them up. And how do we work this out? 2dx plus, multiply this out, d squared minus d minus 6x equals 0. Next, we can rewrite this as d squared minus d plus 2d minus 6x equals 0. So that's d squared plus d minus 6 equals 0. This one can be factored as d plus 3d minus 2. And then what we call the auxiliary equation has solutions. M1 is like d equals -3, so that's M1, and M2 is the 2. Then the solution to this differential equation is C1 for the x's, not for the y's. So x, because I'm solving for x first, x equals C1 e -3t plus C2 e to the 2t. That's the x. Remember, we need to get x or x of t and y or y of t. So I was able to solve for the x because I eliminated the y. Now let me write the system again and see what we're going to be doing for to solve for y. To solve for y, I have to eliminate the x. So to do so, you multiply the top by d minus 3, the bottom by d, and then subtract. D times d minus 3x plus d plus 2 times d plus minus 3y equals 0. And d times d minus 3x minus 2dy equals 0. What do we get when we subtract? The x's will cancel. And from the top one, I get d squared minus d minus 6y. And the bottom one, 2dy equals 0. So that would give us d squared plus d minus 6y equals 0, which is pretty much the same as the previous for the x, d plus 3d minus 2. So the auxiliary equation, m1 is -3 and m2 is 2. So then what do we get? We get y or y of t equals C3, because we already used C1 and C2, C3e -3t plus C4 e to the 2t. So notice something here. We're dealing with first order differential equations or first order derivatives. So this means x and y both of first order derivative as it's given in the system. So what does that mean? That means we should have two constants, not four. So far we use C1, C2, C3, C4. We have more than what we need. So we eliminate. So elimination of sum of the constants needed. So elimination of the sum of the constants are needed. So how do you do that? We choose one of the equations, one of the two given equations in the system of equations, and substitute the obtained x and y, the solutions we just found, the ones that I boxed. So substitute x of t and y of t into one of the equations. So I'm going to choose dx plus the d plus 2y equals 0 equation. And let's see what we get. If you look back at x, we can substitute it here, which is C1 e -3 negative Yeah, negative 3t plus c2e negative 2 plus 2t plus d plus 2, and y is c3e negative 3t plus c4e to the 2t equals 0. Then when you find this, basically what d is saying, it's an operator and says, hey, find the derivative of this thing. Okay, and so the derivative of the first one is negative 3c1e negative 3t plus 2c2e to the 2t plus. How do we deal with this operator here? We take the derivative of all of them and then multiply everything by 2. It's kind of like a distribution. So d for that is going to be negative 3c3e negative 3t plus 2c4e to the 2t plus 2c3e to the negative 3t plus 2c4e to the 2t equals 0. And now what I'm going to do is, as you notice, some are e to the negative 3t and some are e to the 2t. So we're going to collect like terms and let's see what we get. Negative 3c1 minus c3e to the negative 3t plus 2c2 plus 4c4 e to the 2t equals to 0. Then we can solve. In order for this to be 0, we know that the e's are always positive. So in order for this to be 0, the parenthesized quantity for each must be 0. So solve for c3 is negative 3c1, and here solve for c4. c4 is negative 2 over 4, which is 1/2 c2. Why did we solve for them? Well, because we need to go back and replace in y of t, because x of t stays the same, the c1 and c2. But for y of t, we replace the c3 with negative 3c1 e negative 3t and c4 with negative 1/2 c2 e to the 2t. This is the actual solution to that system of equations. Now, for this specific example, and it can happen oftentimes, and not all the time, you know how when we eliminated the y, we had to go through the process. Let me go back up and show you. When we had to eliminate the y, we had to multiply by d minus 3 the first one and d the second one. And then from there, we had to get another equation with operators in y, and then find the auxiliary equation, solve for it, get the solutions, and then go through the whole process of eliminating the stuff. For this specific problem, if you look at the second equation, we could solve for y in terms of x, like so. It's easy to do that. And then what you can do, because we already found what x is. So we already found what x is. So all we have to do is find the derivative of x and then minus 3 times the whole x. So that would give us the derivative is negative 3c1e negative 3t plus 2c2e to the 2t, and then multiply the negative 3 in, so minus 3c1e negative 3t minus 3c2e to the 2t. And if you multiply the 1/2 in and group the terms, that will give us negative 3c1e negative 3t minus 1/2 c2e to the 2t. Isn't that easier? Much easier, right? Much easier method. But again, as I said, this doesn't happen all the time. It's just we were lucky just in this system. Now we're going to look at another example. But in this example, let's see what we have. Solve x prime minus 4x plus y double prime equals t squared, and x prime plus x plus y prime equals 0. There will be more work to do here. So again, the first thing we always do is rewrite this with the operator d, so you can x prime is dx, 4x stays the same, y double prime is d square y equals t square. The second one is dx plus x plus dy equals 0. That's the first thing we always do. And next, we are going to group the d minus 4x together, d squared y together equals t squared, and here d plus 1x and dy equals 0. Any questions about this? So after the grouping, we would like to eliminate. Let's say I want to eliminate the x's. So I'm going to multiply this by d plus 1 and this by d minus 1 and then subtract, right? And then subtract. Let's see what we get. D minus 4 times d plus 1 x plus d squared times d plus 1 y equals d plus 1 t squared. Don't forget the right hand side. And here d minus 4 times d plus 1 x plus d times d minus 4 y equals 0. That's where we're gonna subtract them, and let's see what we get. Where the x's will cancel each other. We have no x's anymore. For the y's, we're gonna get d, if you distribute this, dq plus d squared y minus d square minus 4dy equals d plus 1 t square. D plus 1 t square. And so here what we get is dq plus d squared minus d squared plus 4d, all this y equals d plus 1 t squared. Okay, so these cancel each other. So what do we get? dq plus 4d y equals, the derivative of t squared is 2t and 1 times t squared is t squared. So from the first one, notice this is not 0 on the right side. So the auxiliary equation would be mq plus 4m equals 0. Factor m out, m squared plus 4 equals 0. So then what do we get? We get m equals 0, or m equals, so called m1, m2. m2 is plus negative 4 square root of that 2i, so it's a plus 2i, and m3 is negative 2i. So then we can find the complementary solution yc using c1 e to the 0 is 1 plus there's a complex stuff here, so there's a c2 cosine 2t plus c3 sine 2t. Why did I do complementary? Because the right hand side is not 0 again. So that's how we get the complementary. Now we find what? We now find the particular solution using what? Undetermined coefficients method. And how do we do that? Well, notice the right hand side was dq, like it was the third power. So the y particular should be atq plus pt squared plus ct, plus ct. Now y prime would be 3at squared plus 2bt, y double prime 6at plus 2b, and y triple prime is 6a. Now we look back at the last equation we got here, this one. It's kind of like y, this is like y cubed plus 4y squared, right? So this looks like y triple prime p plus 4y prime p is equal to t squared plus 2t. Y triple prime was 6a. 4 times y prime, 3at squared plus 2bt. Keep the right hand side the same. Then we multiply this out, you get 12at squared plus 8bt plus 6a equals t squared plus 2t plus nothing, like 0. Now we compare coefficients, we get 12a is 1, 8b is 2, and 6a is 0 at the end. But that 6a doesn't do anything. So a here is 1 over 12, b is 1/4. Now how about the c? Maybe I forgot something here. Oh, I put the y double prime. That should be y prime here. Okay, so that should be y prime. So that's a c here. So 3a t squared plus 2bt plus c. So the 12 stays the same, the 8 stays the same, 6a the same, plus 4c. So there's a 4c missing. So here we got 6a plus 4c equals to 0. So, but we found a, so from here 6 times 1 over 12 plus 4c equals to 0. That's 1/2. 1/2. Multiply everything by 2 and solve for c. c is negative 1/8. By finding these, then the y particular would be a t cubed, so this, b t squared, and ct. And from this and the y complementary, we can get the solution for y. Y complementary what plus y particular. Y complementary, it was c1 plus c2 cosine 2t, as far as I remember, plus c3 sine 2t, and the particular we just found it. 1/4 t squared minus 1/8 t. See? Interesting, right? But remember, this is only y, or y of t. If you like to put y of t, is fine. This is just y. We need to find the x now. Now we eliminate y to get, I'm sure all of you know how to do that now, to multiply. I got d squared plus 4 x equals negative t squared. Again, because it's not 0, we have to find the particular and the complementary solutions. From the auxiliary equation, you get m squared plus 4 is 0, so m is plus or minus 2i. So x, not y, x complementary is c4, because I used c1, c2, and c3 already. c4 cosine 2t plus c5 sine 2t. For the particular, we use the undetermined coefficient method. Because the left hand side is of a d square, we're going to find xp, x prime p, x double prime p. xp is at squared plus bt plus c. This is 2at plus b, and this is 2a. And we're going to go back and substitute all of this in here. Solve. I got a to be negative 1/4, b 0, and c 1/8. So y particular would be negative 1/4, t squared plus 0t plus 1/8. So then the y equals y part complementary plus not y here, x. We're used to write y all the time. That's why a lot of us would come to the point like, oh, okay, write y all the time. xc plus x particular. And let's see what we get. xc is c4 cosine 2t plus c5 sine 2t for the particular negative 1/4 t square plus 1/8. That's x or x of t. Now remember, as we did in the previous example, we would like to reduce the number of variables. We like to reduce the number of variables. To do so, to reduce the number of constants, number of constants used, we choose one of the equations. So I'm going to choose the second equation because it doesn't have a t in it. It's easier to work with. So x prime plus x plus y prime equals 0. And let's see, x prime, basically you take this boxed answer and find the derivative for it, which is negative 2 c4 sine 2t plus 2 c5 cosine 2t minus 1/2 t plus 0 plus x itself, which is c4 cosine 2t plus c5 sine 2t minus 1/4 t square plus 1/8 plus y prime, I'm looking at it here next to me, it's negative 2c sine 2t and then 2c3 cosine 2t plus 1/4 t square plus 1/2 t minus 1/8, and the right hand side of the equation is 0. And let's see what we get for this. Negative 1/8 and 1/8 cancel each other. 1/4 t squared and negative 1/4 cancel each other. 1/2 t and negative 1/2 t cancel each other. Magic. Now the only thing left, sine 2t and cosine 2t. So here we have 2c5 plus c4 plus 2c3 cosine 2t plus negative 2c4 plus c5 minus 2c2 sine 2t equals to 0. So now in order for this to be 0, the 2c5 plus c4 plus 2c3 equals to 0, and negative 2c4 plus c5 minus 2c2 equals 0. And what I'm going to do is, if you look at what can be eliminated here, or what kind of relation we can get. Maybe I want to eliminate the c4, so multiply by 2 this. 4 c5, 2 c4, 4 c3 equals 0. Negative 2 c4, c5 minus 2 c2 equals 0. These cancel each other. So that gives us 5 c5 plus 4 c3 minus 2 c2 equals 0. So c5 is 1/5 2 c2 minus 4 c3. If you substitute this back in here, let's say, and solve for c4, because I want to eliminate c4 and c5. Solve for c4, we get, what do we get? c4 is negative 1/5 4c2 plus 2c3. Then rewrite, obtain solutions, right? Didn't we obtain solution for x and y? So when we rewrite them, let's see what happens. X of t is, I'm going to replace the c4 with negative 1/5 4c2 plus 2c3 cosine 2t and 1/5 2c2 minus 4c3 sine 2t minus 1/4 t squared plus 1/8, and y of t is c1 plus c2 cosine 2t. All this stays the same because there's no c3 or c4 in here. C4 or c5, plus 112 t cubed minus, or plus 1/4 t squared minus 1/8 t. These are the solutions to this one. In this section also, we introduce another method here to solve ordinary differential equations with the constant coefficients using determinants. And before I do this, I'll show you this method. Recall several things. If you want to find the determinant of A, B, C, D, something like this, the vertical slashes or bars means determinant. We multiply A times D minus B times C, like that. That's the determinant of 2 by 2 matrix, if you remember matrices. That's one thing good to know. Another thing good to know is called Cramer's rule. Recall this if you've never seen it before. Cramer's rule said if you have a system ax plus by equals, say, like m, and cx plus dy equals n. How do we solve a system of equation like this using Cramer's rule? So Cramer's rule said you can define d to be a, b, c, d, and find what that is, ad minus bc, and assume it's not zero, because if it's zero, the system might have no solutions. So d here, and then you find dx, we call it dx, has not to do with derivatives here. You replace the coefficients of x with the m and n, so mn bd, and you can finish it up, md minus bn, and then you find dy. dy is keep the coefficient of x the same, but since it's dy, we replace the coefficients of y with m and n. So that's an minus mc. We teach this in algebra, like in middle school. So after you find all this, remember we're solving for x and y. So x is going to be dx over d, and y is going to be dy over d. So if you want to write this out in terms of determinants, dx was mnbd, and d is abcd, and y is acmn over abcd. That's how you find x and y using Cramer's rule. We can do same thing here in matrices, or sorry, in differential equations, as we do in matrices. We can start by saying if we are given a system like this, call it L1x plus L2y equals g1 of t, and L3 of x plus L4y equals g2 of t, where those L1, L2, L3, L4 are differential operators. Like d squared, things like that. D is a differential operator. So then how do you find or solve for x and y in these equations? So x would be using Cramer's rule. Because I'm doing x, I replace the coefficients of x with the functions, or g1t, g2t, and keep those for y the same. For here, that's L1, L2, L3, L4. And y equals L1, L3, g1 of t, g2 of t. And then this stays the same, L1, L2, L3, L4. Provided that the determinant of this is not zero. So what we can do here, it's kind of like cross multiply. We can move this all the way here, and the same thing with this, move it all the way there. So we say that the system can be uncoupled into two nth differential equations in x and y. So the system can be uncoupled into two nth order differential equation in x and y. In x and y. So as I said, we move that determinant in the denominator up next to x, and same thing next to y. And what do we get in this case? We get L1, L2, L3, L4 x equals g1 of t, g2 of t, L2, L4, and we do the same thing for the y, L1, L2, L3, L4, y equals L1, L2, g1 of t, g2 of t. Notice when we solve this, assume like the right hand side when we take it as a 0. These two, the good thing about that both of them give complementary solutions, same complementary solution. So less work for us to do. Now we need to look at an example to be able to see how this works. So solve x prime equals negative 3 minus 2y, x prime plus y prime equals 1/2 e to the negative t plus x plus y. So first, as always, we rewrite this in terms of the operators. So dx, bring the 2y to the left side, equals negative 3. And then we have a dx, and there's x on the other side. So you move it to the left or subtract it, you get d minus 1x. And for y prime is d, and there's another y on the right side. Y equals 1/2 e negative t. And remember how we wrote down L1, L2, L3. So there's a d2, d minus 1, d minus 1. X equals the determinant. We replace the d, or the coefficient on the left side, with negative 3, 1/2 e to the t, negative t. And here what we have is 2 and d minus 1. So now, what does that give us? It's d minus 1 minus 2 d minus 1 all x equals negative 3 d minus 1 minus e to the negative t. d squared minus d minus 2d minus 3d plus 2x. Here the derivative of negative 3 is 0. Negative 1 by negative is positive 3 minus e negative t. Then we can factor out this as d minus 2 d minus 1x equals 3 minus e negative t. On the left side it has solutions 2 and 1 to help us find the complementary solutions. So xc in this case is c1 e to the 2t plus c2 e to the t. Those are the complementary. Now for the particular solution, look on the right hand side. That looks like that's in the form of a plus b e to the negative t. Since the left hand side has second derivative, we have to find x prime and x double prime. So that's a 0 minus b e negative t. Also x double prime, that's a b e negative t. So now we go back and substitute into this last equation we got. xw prime, it's be negative t plus, where we have the 3d, so we get 3b negative t plus 2a, so I substituted the second derivative, minus 3 times this one, plus 2 times the 2be negative t, and the right hand side stays the same. And now we can factor the terms involving, so these two combined to 4, actually there's 6, because all these terms combined together. 6b to the negative t plus 2a equals negative negative t plus 3. And if you set them, 6b is negative 1 and 2a is 3. So b is negative 1 over 6 and a is 3 halves. A is 3 halves. So then the particular solution would be, we said it's a is 3 halves, plus b, which is negative 1/6, e to the negative t. And the final answer for x, or x of t, is xc, which is c1 e to the 2t plus c2 e to the t. Then x particular, 3 halves minus 1/6 e to the negative t. This is x of t. A lot of people, when they solve it, they stop here. It's not done. We still need to find the y, or y of t. Well, in this specific example, when I looked at it the first time, I said, you know what? We're lucky. To find y, I looked at the first equation, the x prime equals negative 3 minus 2y, and I just used this box answer that I just got for x, and I found its derivative, which is 2c1 e to the 2t plus c2 et plus 0 minus plus 1/6 e to the negative t equals negative 3 minus 2y. And then all I had to do is solve for y. So 2y to this side, negative 3, and the other stuff to the other side, e to the 2t minus c2 e to the t minus 1/6 e to the negative t. Divide everything by 2, you get negative 3 halves minus c1 e to the 2t minus 1/2 c2 e to the t minus 1 over 12 e to the negative t. But let's say someone could not see this. A student couldn't see that, hey, I can just go ahead and use one of the equations and substitute and get it done with. I don't have to do a lot of work. In this case, what we do is, remember when I said, if we go back up, I said that the circled part, they're the same. So when I find it for x, I get it for y automatically, the left-hand side, or vice versa. If you get it for the y, you get it for x. So for x, when we did all the work, we got this, d squared minus 3d plus 2x. We do the same thing. We're going to get the same thing for this. So here, I don't have to do determinant again. I got the same thing as the previous one. So this is the same as before, as happened in x. But then there's a determinant we have to work with, dd minus 1, and replace the y thinking with negative 3 and 1/2 e to the negative t. Then again, this is d minus 2, d minus 1, y equals, derivative of this is negative 1/2 e negative t. Derivative of that, 0 plus 3, plus 3. Wait, was it 3 or negative 3? Okay, so remember when we do determinant, we do this by times this minus, there's a minus. So minus, so that becomes positive 3 with the minus, it makes this minus 3. It makes it minus 3. So then what we have, the y complementary, not x complementary, is y complementary. We use C3 because we use C1 and C2 already. C3 e to the 2t plus C4 e to the t. And now to get the y particular, look at that, it looks like the previous one. Let's say C plus DE negative t. And we need to find y prime and y double prime. Negative DE negative t and DE negative t. Then substitute those back in. I got 6d to equal negative 1/2 and 2c equals negative 3. So d was negative 1 over 12 and c is, that's a capital C, negative 3/2. So after we found those, that gives us y of t, because I have the complementary already, C3 e to the 2t plus C4 e to the t. And the particular, it's C and then d e to the negative t. That's the y of t. So I found x of t, y of t. But remember, one last step here is that we need to reduce the number of constants in our solutions. So we reduce the number of constants by substituting x and y into one of the given equations. Let's say the first equation, x prime equals negative 3 minus 2y, which can be rewritten as dx plus 2y equals 3. So when we find the derivative of x that we found earlier, we get 2c1 e to the 2t, c2 e to the t, plus 1/6 e to the negative t, plus 2c3, if you multiply the y's, 2t, plus 2c4 e to the t, minus 3, minus 1/6 e to the negative t equals negative 3. Notice negative 3 cancel each other. These cancel each other. Now we collect the ones for the 2t, e to the 2t and e to the t. So we have 2c1 plus 2c3 e to the 2t, c2 plus 2c4 e to the t equals to 0. Now to solve for that, from here we get c3, which is negative c1. And C4 is negative 1/2 C2. Negative 1/2 C2. So then we substitute them back in. So x of t, it's C1 e to the 2t plus C2 e to the t plus 3/2 minus 1/6 e to the negative t. So it stays the same. But in y of t, we need to get rid of the constants C3 and C4. So replace C3 with negative C1, so negative C1 e to the 2t. Replace C4 with negative 1/2 C2 e to the t, minus 3/2 minus 112 e to the negative t. These are the solutions. Notice something here that I'm going to highlight, this part, the solution for y of t. After you copy it down, I'll show you. So this answer, if you look at this one and this one, they match. This one was found kind of like using a shortcut, but the other one we had to go through the whole process again. They match. So basically this section covered two different ways, using determinants to solve differential equations, and one using operators. So operators with elimination or system of elimination, and the other one the use of determinants to solve differential equations.